Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to go over solutions and the different ways of calculating the different concentrations. How do you put your concentrations and what units do you put them in, and how do you express them? So there's a lot of different ways, the different formats for your answers when you're calculating concentrations. Some units are better than others depending on their usefulness, and different branches of chemistry tend to use different types of units. They tend to lean towards different types of units because those are the units that they typically use in those areas. So I'm going to show you in this video different ways of expressing concentration and how they're used. Okay, but before we get to that, we need to talk about some assumptions that you most likely are going to need to make if you are not given enough information. So what are these assumptions? So I have them written on the board here. So what assumptions are you going to want to make? Unless you're told otherwise, you should make these assumptions. So if you're given a problem to work on, or you're working on something that needs to be solved, and you're not given any more information, then you would assume, one, that the solvent that you're using is water. So if you're talking about concentrations of things, then assume otherwise, that your solvent is water. So it is the universal solvent. It is what is most commonly used, especially for your polar substances. If you're going to dissolve something that's polar or ionic, you're most likely going to be using water. So that's the assumption you're going to want to make, unless you're told otherwise. If you're told that the solvent is something else, like maybe an alcohol or say carbon tetrachloride or something like that, then go with that. But if they don't tell you anything about what the solvent is, then just assume it's water. The other assumption is that unless you're told otherwise about the density of your solution, assume that it has the same density as water. And the density of water, you should know, is 1 gram per 1 milliliter. And I think that's at 25 degrees Celsius to be, pretty exact. But just assume that that's the density of your solution, unless you're told and given the density of the solution. So these are a couple of assumptions you're going to want to make when you're doing your calculations and solving problems. Okay, so the next part I want to get into is the different kinds of ways in which you can represent the concentrations. And so hold on tight for that. Okay, welcome back. So I'm going to start to go over the different ways of expressing concentrations. So let's get into this. So the first one I'm going to talk about is mass percent or percent composition. So mass percent is where you express the concentration as a ratio of masses that's expressed as a percentage. So let's review what a percentage is. So a percentage is where you take part of something and you divide it by the whole of that thing and multiply it by 100. So to just remind ourselves that percent means per 100. That's what the cent means in percent. If you remember, say century. Century is a 100-year time span. So cent is referring to 100. So percent means per 100. So to get a percent, you're taking your part and you're dividing by a whole and you're multiplying that by 100. That's going to give you your percent. So when we're talking about mass percent, the part and whole are expressed in terms or units of mass. So remember, so one of the things that I want to point out is that solution, you have to remember that a solution is a solute added to a solvent. So it's a mixture. So a solution is a mixture, a homogeneous mixture, if you remember. And if you remember, homogeneous mixtures are mixtures that are uniform. It means that when you look at them, they only look like one substance. They don't look like a mixture because everything is mixed together uniformly, equally. And so when you look at it, it looks like one substance, but in reality, it's a mixture of a mixture of two or more substances. In this case, a solution is specifically going to be a solute or multiple solutes, perhaps, mixed together with a solvent, and the two together give you a solution. And so this is our part. The solute is the part that we're getting the percentage of, and the solvent plus the solute is the whole. So the solution is the whole, and the part that we're looking at is the solute in most cases. And I'll show you an example where that's not the case. There's at least one case in which the solution is not going to be the whole that we are looking at. That's not going to be the whole. Okay, so in mass percent, the part that we're looking at is the solute, but in terms of mass, and that's going to be divided by the mass of the solution, whatever that is. And the masses are normally going to be in grams, but not necessarily grams. It could be in kilograms or whatever unit that is being used or that is convenient at that particular time for whatever reason. So you take the mass of the solute, divide that by the mass of the solution, and you multiply by 100. And so this is expressed as percent M over M, mass over mass, right? You could also express these mass percents, or I should say percent composition, as a percent volume. In this case, instead of having mass of solute divided by mass of the solution, they would be in volume units, maybe milliliters. So you'd have milliliters of solute divided by milliliters of solution, or maybe it's liters, or whatever unit of volume that you're using. The idea is here is that to get the percentage, you're taking the volume of the solute divided by the volume of the solution multiplied by 100. And again, that's going to be usually expressed as percent V over V, or you can have a mixture. You can have a percent mass per volume, where the solute is in mass units and your solution is in volume units. And there you can have a percent mass over volume as well. So, but the focus on this video is percent mass, which is mass of solute divided by mass of the solution multiplied by 100. So anytime you want a percentage, you're going to follow this general formula here for any percentage you want. Okay, the next thing I want to talk about is parts per million. So parts per million is pretty much precisely or exactly the same as mass percent, except the only difference is instead of multiplying by 100 to get your concentration as out of 100 or per 100, you're going to be multiplying by a million instead. So basically what you're getting here is a ratio of masses expressed as 1 out of a million rather than 1 out of 100, which is what a percent is, 1 out of 100. So this is usually used when you want very low concentrations are very important or very significant. This is like in terms of when you're trying to measure the amount of a poison that's in a solution, or a measure of a pollutant that's in a solution. Usually very low concentrations are significant and can cause harm or health problems. So, for example, like mercury, right? So, if you very, very low levels of mercury can cause problems. Heavy metals can cause problems. So, you don't want that in your drinking water. So, the water companies are usually measuring those concentrations in terms of, excuse me. Sorry about that. So the water companies are usually measuring those concentrations in parts per million, right? So to calculate the ppm, which is your abbreviation for parts per million, ppm is the part divided by the whole multiplied by a million. And so in this case, you're looking at mass. So we take the mass of the solute divided by the mass of the solution, and then multiply that by a million to get a nice number. And so usually the mass of the solute is going to be very, very small. So in order to get a number that's workable, like in 1 part per million or 100 part per million, you got to multiply by 100 to get a reasonable number to work with. Otherwise, they're going to be really, really small numbers. And so this is more convenient to work with when you're dealing with very small concentrations. Another concentration that I don't have written down is parts per billion, right? So ppb would be expression for that, or the abbreviation for that. And again, as you can guess, parts per billion is going to be expressed as part divided by the whole, which is going to be, again, mass of solute divided by mass of solution. Instead of being multiplied by a million, it's multiplied by a billion. So those are even smaller concentrations that you need to multiply by a billion to get a workable number that's convenient to use. And so again, normally it's mass over mass, but again, you could have volume over mass. Volume, mass over volume, or volume over volume, or something like that. But typically, it's mass over mass, and the units of mass are whatever's convenient, usually grams. Okay, so that's the first two. I'm going to continue with the next few in just a moment. So hit sit tight. Okay, so the next two ways of representing concentrations is grams per liter and the mole fraction. Sorry, I forgot what I was going to talk about. Okay, so here we go. So number 3, grams per liter. So what is grams per liter? Grams per liter is the ratio of mass of solute to the volume of solution. This is easy for when you're measuring a solid solute dissolved in a liquid. This is often used in testing solubility, and it's a quick and dirty way of calculating things. It's a unit that's used when you really don't need precision all that much. You just need an estimation of a solution that you're going to use for something that doesn't require precision. It's going to be used for something that you're going to be for something else. Like so, for example, in biology, you're not going to be really focused on the solution itself, but what you're going to be using the solution for. So if you need a quick and you're making a lot of volume of this, so if you're creating liters of this solution, you just want to measure out a certain amount of solid really quick, dissolve it in a certain amount of solution or solvent to make a certain amount of solution that you're going to be then using for your biology purposes. So if you're making, for example, a culture solution or something like that, you're probably going to be measuring grams and then dissolving that into a certain amount of your liquid. Now, for the biology peeps out there, if you have any thing to say about that, or if you want to correct me or add to what I'm saying and give me examples of where I might be mistaken, or maybe examples of where I'm right, then please put them down in the comments below. I'd love to hear from you. But for chemistry, we're not really going to be using this because we're really are focused on making a precise solution that we're going to be using in chemistry that really requires us to have the right concentration. So we're not going to be using this very much in chemistry, but this is used in science. So grams per liter would be the mass of the solute divided by liters of solution. So specifically liters, so you must have liters. And the mass can be usually grams. So again, notice we have solute over solution, so we're getting a ratio. This time we're not multiplying the ratio by anything to get per 100 or per 1 million or per 1 billion. It's just a fraction. So we're using a fractional amount here. Okay, what the next one is the mole fraction. Again, a fraction. We're not multiplying this by anything. It's just we're getting a fractional ratio. And this mole fraction, as the name suggests, just like the name up here suggests what our units are going to be, or what we're getting the ratio of. Here we're getting the ratio of moles. So here the ratio is going to be the moles of solute, which we're calling N sub A. So remember, little n is the symbol that is often used in chemistry for representing moles. So N is for moles. Here we got Na, substance A, which we're calling our solute. So it's going to be the ratio of the moles of solute, Na, to moles of the total solution. So total moles of solution, which again, remember that the solution is the solute plus the solvent. So we're going to be adding together the moles of the solute to the moles of the solvent, and that gives you the moles of the solution, the total moles of the solution. And so when we calculate the mole fraction of a certain solute, if you have multiple solutes, right, you can get the mole fraction of each as long as you know what the total moles of everything mixed together is. So if you want to get the mole fraction of A that's in your solution, that is represented by this funny looking X. This is the Greek symbol chi. So this is often used for mole fraction. So you have chi sub A is equal to the moles of A divided by the total moles of A plus B, the solute A plus solvent B. And so you can have multiple solutes. So this could be Na plus Nb plus Nc and so on. So as long as you know what the total moles in the mixture are, you can get your mole fraction. So it's the mole of the substance you're interested in divided by the total number of moles, and that gives you the mole fraction of that substance. So that's mole fraction. So next thing I'm going to be talking about is molarity, which is the most important one that's used in chemistry. And then I'll also talk about molality, which is a little bit different. It's related but different, and I'll talk about those next. Okay, welcome back. So the next two ways of expressing your concentration is molarity and molality. So what is molarity? Molarity is a ratio of moles of solute to liters of solution. So this is similar to grams per liter that I talked about earlier, but this is basically converting your grams to moles first and then taking the moles and dividing that by liters of solution. This is more commonly used in chemistry than the others because it has your solute in moles, which is what a chemist is mostly interested in because we use moles a lot in conversion. So if you're ever doing stoichiometry, you need moles in order to convert from one thing to the other. It's just a very convenient unit to be using in chemistry. And so we're always trying to get to moles. And so molarity is expressed in this way. We use capital M for molarity, and that is moles of our solute divided by the liters of solution. And then lastly, we have molality, which is similar, looks and sounds similar to molarity, but it's molality. And it's often referred to as the molal of concentration or molal concentration. And here we're taking the ratio of moles of the solute, and we're going to get that with relation to kilograms of solvent. So it's moles of solute to kilograms of solvent. So I underline this because notice that we're not using solution, which is the case for all the other ways we've been expressing concentration. It's always been part to whole, where the whole is the solution. In this case, it is the solvent. So you got to be careful when you're doing molality. Is you got to remember it's kilograms per solvent. And that's the other thing I want to point out. It's kilograms, not liters. It's not a volume. It's a mass, and specifically it's kilograms. So kilograms of solvent. And so this is often used when we're expressing concentrations of solutions that are related to vapor pressures and temperature changes. So the reason that this is better in this case is when we're using kilograms. When you're using volumes, volumes can change depending on the temperature, right? So at high temperature, low temperature, your volume can change, and that would change your concentration, which is something you probably don't want in certain situations. So when you're trying to measure the concentrations of solutions related to vapor pressures, well, vapor pressures, volumes can change depending on temperature. And so you want to avoid any type of changes in your solution with regard to measuring the vapor pressures and things like that. So normally you're going to be using molality when you're measuring boiling points or melting points and other colligative properties of solutions. So colligative properties are properties in which the concentration, which the property you're measuring is dependent upon the concentration of the solute. So for example, melting point or let's say boiling point of a solution, well, that's going to depend on how much solute you have dissolved in your solution. So that's going to be important. So I'll talk more about colligative properties in another video, but that's a good intro to what colligative properties are. And so when we calculate molality, molality is represented by the small m, and it's usually italicized. I try to italicize it as best as I can, but it's an italicized small m, and it's moles of solute divided by kilograms of the solvent. Okay, so that's it for this video. In my next video, I'll go over a couple of example problems of how to calculate molarity. But in this case, I've gone over all of the expressions of concentration that I want to go over. There's other ways of expressing concentration, but these are the main ones. I hope you found this video interesting and enlightening, and I hope informative. I hope you learned something from this video. If you did, in any way, then please make sure you like the video, hit that like button. Also, make sure you subscribe to my channel, hit that notification bell, and when you do, make sure you click all so you can be notified by all the videos I put out. Also, make sure you put a comment down below in the comment section. Let me know what you think, ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.